sustainable development. So now Dr. Marie Alexandre will be moderating the session, who is a senior scientist at French National Center for Scientific Research, based in the Oceanography and Climate Laboratory, Experimentation and Numerical Approaches in Paris. And Dr. Marie Alexandrine earned a PhD degree in Marine Sciences from the Pierre and Marie Curie University in Paris. And over the past 15 years, she has been working in the role of ocean on climate variability. She also served as a squad president from 2016 to 2020 and also a co-chair of IIOE2 steering committee. So now I hand over the floor to Dr. Marie Alexandrine to carry out the session.
Thank you very much, Anish. Can you hear me clear and loud?
Yes, you're loud and clear.
Thank you. So I would like to call our first speaker. So as you just explained, we'll have 4 speech or keynote speech that will be given today, followed by the presentation, a discussion of the panel. The first of the speaker is Michael McFadden, and I would like to quickly introduce him before he starts giving his 20 minutes presentation. Dr. McFadden is the director of the Global Tropical Moored Buoy Array Project Office at the Pacific Marine Environment Laboratory of NOAA. Dr. McFadden is a well-renowned scientist working in the field of oceanography and ocean modeling. He earned his PhD in physical oceanography from Scripps Institute of Oceanography in 1918 on model of the equatorial ocean circulation. Dr. McFadden has several honors and awards in his name, including the Sverdrup Gold Medal from the American Meteorological Society, Fridtjof Nansen Medal from the European Geoscience Union. He's also a member of several professional societies, including the Oceanography Society, American Geophysical Union, the American Meteorological Society, the European Geoscience Union, and Marine Technology Society. Michael is also a member of was a member of the IPCC, who shared the Nobel Prize in 2007 for contribution for the assessment report. So without further ado, I will give now the floor to Michael. And as you said, his presentation, or maybe I should remind the title of his presentation is on Advances in Describing and Understanding Equatorial Indian Ocean Circulation. The floor is yours.
Thank you. Thank you. Let's see. Can you hear me?
Yes.
And can you see my first slide?
Yes, full screen. That's
yes.
You can...
Okay, great. Actually, I changed the title of my presentation to Volume Transports in the Shallow Overturning Circulation of the Indian Ocean. And but first, let me say thank you for the invitation to present at this conference. It's regrettable that we can't be together in person, but virtual is the next best thing, and I'm happy that I can participate. So what I would like to do is really, I want to showcase observations from INDUS. INDUS is a collection of in situ observing components that was designed to complement the constellation of Earth observing satellites. And in particular, what I want to do is quantify volume transports at 3 choke points in the shallow overturning circulation of the Indian Ocean. And these will be the cross-equatorial flow in the interior, upwelling in the Somali Current, and upwelling in the Seychelles Chagos Thermocline Ridge region. And the 3 observing systems I'm going to highlight here are Argo, Brahma, and the surface circulation drifters, and to show the synergies between them. So the shallow overturning circulation, I should preface by saying the circulation of the Indian Ocean is unique in that it's blocked at 20 north by the Asian landmass. And so this leads to a vigorous monsoonal circulation in both the ocean and the atmosphere, and hemispherically asymmetric shallow overturning circulation in the upper ocean. And this shallow overturning circulation is shown in these 2 schematics. On the left is a latitude depth section. And basically what we have is sinking water in the subtropics. subduction from downwelling favorable winds, and this flow returns to the north. A deep component of it crosses the equator, upwells in the Somali Current region and other upwelling centers, and then returns southward in a shallow surface layer. There's a second component to this circulation we call the southern subtropical cell, where subducted water in the subtropical thermocline upwells in the Seychelles-Chagos thermocline ridge region and then returns south. This is the plan view, and you can see the subduction region here, south of 20 South. Water entering into the thermocline migrates towards the equator, crosses in the Somali Current and upwells off of Somalia and Oman, and then returns in a broad and diffuse return flow in the interior ocean. That's the cross-equatorial cell. And then the second branch of upwelling here in the ridge region is a part of the southern subtropical cell. So this is important not only for understanding the mass balance of the ocean circulation in the Indian Ocean, but also for understanding the heat balance, the distribution of nutrients that affect biogeochemical cycles, the carbon cycle, ecosystem dynamics, and fisheries. And so this subtropical, shallow overturning circulation is really central to many of the problems that we're interested in with regard to Indian Ocean oceanography. So let's start with cross-equatorial volume transport. And one way to estimate this is from the Sverdrup relation. This is a theory, simple theory. It says that the depth integrated meridional velocity is proportional to the curl of the wind stress. And what's shown here is a 40-year average of trop flux wind stresses. Those are the vectors. And then the color contours here are the meridional transport per unit width in units of meter square per second. And you can see it's southward everywhere, virtually everywhere in the interior ocean, up to about 15 to 20 degrees south. So this provides one estimate. Now, it's a wind product, though, and it's based on a theory. So how much can we trust it? There is one location where we can directly estimate the depth integrated meridional velocity, and that is from an ADCP array of moorings along 80 East. And this was an array that spanned from 4 south to 2.5 north. Most of these elements were in for 5 years or more. The equatorial site right here is still operating now. So this record I'm showing you is 10 years old, but it's actually longer. Now, we can make a mean from this section, and it's very important to notice that these red and blue stripes, these are very energetic, biweekly, mixed Rossby gravity waves. They have a peak-to-peak amplitude of about 100 centimeters a second. And what we're trying to pull out of this is a long-term average, here on the right, that is just a couple of centimeters a second to the north or to the south. And here's that mean. You can see the peak is about 4 centimeters a second at thermocline depth. So it's a very small mean signal. You don't see any signature of this mean signal in that long daily time series. So you really need to do heavy averaging to pull it out. So here is a meridional section from all those ADCP moorings. It's the mean 5-year mean section. The red and the blues contours, these are temperatures from Argo. The arrows, white is the 5-year mean. White means southward, black means northward flow. And above here, we have the wind stress curl and the two components of the wind stress. So the theory tells us we should expect southward flow. And what we can do is right on the equator, we can compute the depth averaged meridional velocity. And that is shown here. It's very shallow. It's only down to about 140 meters that we see any significant velocity. We can compare that to the Sverdrup theory. And you can see that within the uncertainties, they agree very well. So what we can do then is we can take the trop flux winds and we can integrate, now that we have some confidence based on this calibration check, from actual observations. We can integrate from the eastern boundary all the way to the western boundary, and we find this at about 7.3 spheredrifts of southward transport in the interior ocean over this time period. And we can see an earlier estimate that Fritz Schaub published 20 years ago is about the same, actually, within the uncertainties, 6.5 he got. And you can compare both of these numbers to the flow in the Somali current crossing the equator in the western boundary. It's about 10 spheredrifts, shot it all, did not put error bars on this. But it's a much deeper flow. It's over 500 meters, whereas the return flow is only in the upper 100 meters or so. So obviously some transport that crosses the equator in the western boundary current has to upwell to return south. Now, I want to go back to this section for just a moment to make another point, and that is that you see, consistent with the spheredrift theory idea, that most of the flow is to the south, these white vectors. But there are some arrows that are pointing to the north. There's northward flow in the surface layer near the equator, and northward flow in the thermocline just north of the equator. Why is that? That's because the mean winds along the equator are positive. It's mean westerly winds, which is in contrast to what we experience in the Pacific and Atlantic Oceans, which are mean easterlies. And so one of the consequences of this, is that we have Ekman convergence in the surface layer from those westerly winds. And those westerly winds pile up water in the eastern Indian Ocean, and it creates a pressure head that leads to a geostrophic divergence at depth. And you can see here the negative dashed contours. These are pressure gradients computed from Argo. This geostrophic flow is occurring over a greater depth than the Ekman convergence. And so the circulation is closed by downwelling, about 1 meter per day. And this downwelling has two important consequences. The first one is you don't see any cold water near the surface in this section. That's because unlike in the Pacific and Atlantic, where we have upwelling, which brings cold water to the surface, here we're converging warm water and pushing it down. And that's illustrated here. You see the cold tongue in the Eastern Pacific and in the Atlantic in these trade wind forced regimes. Here we've got mean westerlies, no cold tongue. The other important consequence is that any water that is subducted into the thermocline in the subtropics must upwell away from the equator, not on the equator, as happens in the Atlantic and Pacific. And so we want to look at some of these upwelling centers in the Indian Ocean and try to quantify their upward mass fluxes. And so for this, we'll use surface circulation drifters. This is a monthly climatology based on 40 years of data, about half of those from the Indus era, beginning around 2000. This climatology was gridded on a quarter of a degree by quarter of a degree grid, and it includes error estimates, so we can try to put some error bounds on computations based on these. And here is the annual mean surface current speed in colors and the vectors in these arrows. And here you can see the Somali current along the western boundary here. You can see the Great Whirl off the Horn of Africa. You can see mean westerly flow. That's because the winds along the equator are on average westerly. And you can see this broad westward south equatorial current. So we want to estimate upwelling from this gridded data set along the Somali coast. And so what we're going to do is we're going to take a little box that's between 0 and 12 degrees north and about 3 degrees offshore. And what we see, and what we see here, these are the mean currents, mean surface currents, and the mean wind stresses in that box. And you can see this very dramatic seasonal cycle, strong winds and currents to the north, to the northeast in the summer and towards the southwest in the winter season. You can see that the currents in blue are always to the right of the winds, which are red, which is what you expect from Ekman dynamics in the Northern Hemisphere. That means offshore in the summer and onshore onshore currents in the winter. So we can compute the flux divergence across these boundaries now from this data to estimate the upwelling, and that's shown here. Basically, we're assuming that the flow in the upper 50 meters is uniform, and then just computing the divergence of the horizontal currents along that boundary, and we get an estimate of upwelling along at the 50-meter level. And you can see it shows a very significant seasonal cycle. This is the error bars on this calculation. Peaking in the Northern Hemisphere summer, which is what we would expect. And you can see the dramatic effect that this upwelling has on sea surface temperature, rapid drop of 4 degrees Celsius between May and July. So if we put some numbers on this, the maximum estimated upwelling here is about 3.5 meters a day. If you translate that into spheredrups by just multiplying the area over which it's occurring, it's about 16 spheredrups of upward mass flux at its peak in the summer season, and an annual mean of about 5 spheredrups. So about half the water that crosses the western boundary in the Somali current at the equator, that 10 spheredrups that Schott reported on, about half of that is upwelled off Somalia. And then that's going to return south in the interior. Schott actually published some estimates of the Somali upwelling 20 years ago, and he found maximum of 12 to 21, which is sort of brackets our estimate of 16, and an annual mean of about 4 to 7, which again brackets our estimate of 5. Okay, so next I want to turn to the Seychelles-Chagos thermocline ridge region and to estimate upwelling there. And I'm going to use hydrographic data for this exercise. And this is from a paper that Matoki Nagura led a few years ago, which is basically an update of a classic paper by Joe Reed on the geostrophic circulation of the Indian Ocean. Reed's publication in 2003 made use of about 2,000 CTD casts. The paper that Nagura led and published a couple of years ago had 2 orders of magnitude more data, mainly because of the advent of the Argo era. So features much, much more accurately defined from this analysis. And so what we want to do is we want to take a meridional section from the equator to 40 south, which cuts through the subduction zone and the upwelling ridge here. And just for reference, this is the mean wind stress curl with the section shown here. The blue is where the curl is upwelling favorable, and that's, as you would expect, near the ridge, upwelling ridge. And the red is downwelling favorable, which of course corresponds to the subduction region. So here we have this meridional section, temperature shown here. The color is temperature, and the contours in black are isopycnals. And you can see where the winds are downwelling favorable, the isotherms and isopycnals bow down. And as we transition closer to the equator and the winds become upwelling favorable, you can see the thermocline ridge developing. The salinity field shown down here, first for reference, this is the wintertime mixed layer. And so what you can see is coming from the subduction zone, a high salinity tongue, which is created by high evaporation in the subtropical high region. That high salinity water is being pumped into the thermocline and it's migrating towards the equator in the upper pycnocline. And at the northern end of this section, you can see another high salinity tongue. This is Arabian seawater that's being advected in the interior by that southward transport that we talked about earlier. And these 2 water masses from the south and the north are converging in the ridge region. And so what we want to do next is we want to look at the circulation on a horizontal plane on the 25.5 kilogram per cubic meter isopycnal. and that's shown here. So here's the subduction region. Water subducted into the thermocline, flows around the subtropical high, moves towards the western boundary, and then recirculates around the thermocline ridge in a cyclonic tropical circulation cell. And over here, we have three separate elements of upwelling in this thermocline ridge region. One is simply based on the wind stress curl. Another is based on the assumption that the linear vorticity balance holds in the thermocline, and we can estimate W from the computed geostrophic velocity using Argo and the CTDs. And this is a similar calculation, but it's using the Aura S4 ocean reanalysis. And these two are not independent because the Aura S4 assimilates Argo, but it's also a combination of Argo and model physics. So they are different. And what you can see, if we compute the upwelling in a box like this, 5 to 10 north and 50 to 90 west, we get 7.5 Sverdrups for the curl calculation, 3.2 for the Argo, and 2.4 for Aura S4. The wind stress curl is larger because it's a smoother field, and these others show a degree of eddying, and that may either be noise or it may be real eddy dynamics. But in any case, we get a range here from about 2 to 2.5 to 7. And Schott in 2002 published an estimate using an earlier and cruder ocean reanalysis, SODA, and came up with 2.8. So our estimates bracket that earlier estimate as well. And then we can add a fourth calculation to this thermocline ridge upwelling transport, and that's using drifters and doing the same kind of calculation that we did in the Somali region, assuming the flow is uniform in the upper 50 meters and computing divergence. And here we're going to estimate between 60 and 90 east, and we'll look at as a function of latitude between 5 and 25 south. And that's shown here. And what you can see, the solid red line is the estimated upwelling or downwelling. It's actually downwelling in the region of near the subtropical high, and consistent with the theory that that curl should be downwelling favorable. But here you can see a very definite peak in upwelling centered around 5 or 6 south. And if we compute the magnitude of that, it's about 0.5 meter per day. And the transports, let's see, the transports, are roughly between 5 and 7 Sverdrups in this region between 60 and 90 east. And so that's a fourth estimate of upwelling in this region. So to summarize then, INDUS observations have allowed for a more precise and quantitative description of the shallow overturning circulation in the Indian Ocean. And it's allowed us to quantify transports at some key choke points across the equator, in the Somali Current region, and in the Seychelles-Chagos thermocline ridge region. And, I've compared these to the earlier estimates that Schott published. And, it raises the question, have these transports changed at all in 20 years? And it's hard to say because Schott's estimates were, they had a high degree of uncertainty based on cruises in many cases or earlier generations of wind stress products or ocean reanalyses. But these estimates that we've made also have some uncertainties, and we really need to improve on these estimates, particularly because we know the ocean is changing, the climate is changing. It will continue to change, and the Indian Ocean is experiencing some of the largest changes in the world ocean. And so this really points to the need to improve not only on the estimates that I showed you, but on many of the measures that we use to quantify the Indian Ocean circulation and its impact on climate. And the only way to do that is to sustain INDUS. We need to sustain INDUS to accurately detect long-term changes, to understand the mechanisms responsible for them, and to improve the models we use for climate prediction, weather and climate prediction, and long-range climate projections. And so that is the message I want to leave you with, that INDUCE has been a tremendous success. It allows us to do novel research, novel computations, and it's a critical asset that we continue into the future. And where there are challenges like we're experiencing with financial, logistic, building capacity in the region so more nations can participate, developing technologies that make measurements more efficient and more multidisciplinary. These are all challenges, but they also represent opportunities. And the UN Decade of Sustainable Development is a auspicious time for us to promote the concept of sustained Indian Ocean observing and to improve it for the future. So with that, I will end, and thank you for your attention.
Thank you, Mike, for your very nice presentation. I see 2 hands raised, but I guess that we'll take the question from the floor after the last speech, together with the 2 items that have been addressed towards the UN Decade. So we will move on to our next speaker, Dr. Sulanoshana Gagdil. She's a renowned monsoon meteorologist and honorary professor at the Center of Atmospheric and Oceanic Sciences, Indian Institute of Sciences, Bangalore, India. She did her PhD in applied mathematics from Harvard University in United States. Subsequently, she worked as a postdoctoral fellow under the supervision of Professor Shami at MIT, United States. Professor Gagdil played an instrumental role in setting up the prestigious Center of Atmospheric and Ocean Sciences at Indian Institute of Science, Bangalore, where she served as a chairperson from 1989 to 1996. Her past breaks research led to the discovery of a basic feature of the subseasonal variation in the monsoon cloud bands. She demonstrated that the monsoon is not a gigantic land-sea breeze, but instead is a manifestation of seasonal migration of planetary wave systems, which is seen over non-monsoonal regions as well. Professor Gagdil served as a member of the scientific committee of WCRP and played an important role in shaping the science plan of the observation field campaigns organized under the umbrella of the Indian Climate Research Program. She published more than 100 research papers in reputed journals and also received several awards and honors. Professor Gagdil, I now call you to the floor and to give your talk. The title of your talk is on the role of the Indian Ocean in the variability of the Indian monsoon.
Good morning. Are you able to see the PPT?
Not yet. We can hear you though.
Good Lord. Okay.
Yeah, is it okay if I share it from here?
1 minute. I think I will be able to manage because we've managed last time, isn't it? Okay. Not able to see it yet. Are you?
Not yet.
But it is sharing. I don't understand. Just see now. Is it? Are you seeing it?
Not yet.
Good Lord. Modern technology. Well, we'll just give it one more try because it would be faster if I can project. But you're still not able to see it, then you go ahead and project. Okay?
Okay.
I think you're not able to see it. Am I right?
You're right. Not yet.
Then you please go ahead and project and I will talk.
Okay, thank you.
Sure.
Now we can see. Can you see it as well?
Yeah, I can.
Yep. Okay. So
Now
the floor is yours. You can start.
Thank the organizers for inviting me to give this talk. And it is prepared with very valuable inputs from Francis, with whom I have done a lot of the work that I will present today. The next slide. is the outline, and I'm not going to go through it in great detail. It is monsoon and Indian Ocean. What are the I'm going to focus only on interannual variation of the monsoon and the important modes for it, one of which is the equatorial Indian Ocean oscillation. Talk a little bit about what governs the variation of organized convection over tropical oceans and the this what governs the pulse of this phase of this equinu, which is very critical to determining interannual variation of the monsoon. But most importantly, we generally like to impress people with a potential use. This time we have used all this knowledge we gained to actually apply this understanding to predict second half of the monsoon of 2019. It was an educated guess based on all the science we know and the new data available thanks to the kind of buoys Mike talked about, and in fact was validated. So I'm going to end my talk with that. The next slide shows in fact that we have published 3 papers on this. First, which gave the speculation in August, and the second which showed the validation, which it turned out to be correct, and a comment by Mark Kane, a very nice one. Next. Okay. Now this is a satellite view of a monsoon day in 2016, and what you see here is a very beautiful band here, which is the ITCZ. So the monsoons responsible, the system responsible for the monsoon is the intertropical convergence zone. And you see it sitting right over India here. But notice that there is a second place where you see the ITCZ, and that is the oceanic ITCZ. Now this is a very special feature of the Indian longitudes, that there are 2 favorable locations of the ITCZ, and there is a competition between these 2 ITCZs. In fact, weak phases of one coincide with active phases of the other, and so on. Okay, the next slide shows that overall in the competition, it is the monsoon TCZ that wins. That is why we can get the monsoon rain over Indian region. And so the primary rain band is the monsoon TCZ, and the secondary band is the oceanic TCZ. Next. But oceanic TCZ is not only harmful for the monsoon, it also helps sustain the monsoon by having these poleward propagations at the interval of 2 to 6 weeks throughout the monsoon season. So it sustains the monsoon TCZ with these propagations from the ocean. So the interaction between the ocean ITC and the monsoon TCZ is very complex. The next one shows you what we are trying to get. We would like to understand and then predict the year-to-year variation of all India summer monsoon rainfall, which is shown here. We have a rich data set, 1870 to 2021. Okay, and the green arrows are excess, which is anomaly greater than 1 standard deviation. Red arrows are deficit. This is droughts. Anomalies, this is deficit larger than 1 standard deviation. So you see, they do occur intermittently. You will not much, though you may like, see any trace of climate change in this. As far as this is concerned, of course, what you see is a decadal variation very prominently, but I will not get into that. But it is extremely important to understand and predict this, what I call ISMR, Indian summer monsoon rainfall, because it has a huge impact on our economy and agriculture. The next slide, and that is going to be my focus today. So I'm going to not talk of all time scales, but variability of monsoon only on the year-to-year or the interannual scale. Now it is well known that the most important factor determining the interannual variation is ENSO, okay? And I choose an ENSO index which is negative of Nino 3.4. So positive values indicate favorable for the monsoon. It is the cold phase of ENSO. And what you see here is a plot of anomaly of ISMR, the rainfall, versus the ENSO index. And what you will see is, by and large, sign of the ENSO index is the same as the sign of the monsoon rainfall. This is what is showing that there is a high propensity for the signs to be the same. And this is why very often ENSO is used as a basis for prediction of monsoon. But note that there are huge exceptions. there are two cases of excess monsoon rainfall, 94 and one more here, which occurred during the warm phase or a weak El Nino of the monsoon, and a drought of 85, which occurred during a cold phase, which should have been favorable, which is almost like La Nina in the monsoon. So we have this drought and this excess monsoon years, which are both exception extremes, which occurred when ENSO should not have, from ENSO we would not have expected it. Next slide shows, next slide. That means that there is one more factor at least, which we have to know to understand the interannual variability. Now that factor happens to be equatorial Indian Ocean oscillation. Okay, and I show it as OLR anomaly patterns. These are the same boxes that are used in Indian Ocean dipole. So this is the West Equatorial Indian Ocean and this is the East Equatorial Indian Ocean. So this positive phase of the monsoon, which involves negative OLR anomalies or good rain over India as well as WEIO, and suppression over EEIO. Whereas the opposite phase involves suppression over this region and enhancement of EEIO. And equatorial Indian oscillation is the oscillation between these two phases. Next. I will not have time to go into this because this equino was discovered in 2004 and there are a lot of papers on it now. Suffice it to say that if we plot equino index here and ENSO index here and color with red or green or red and blue the droughts and the excess monsoon years, then there's a very clean separation between the two. This is saying that we need both these to understand the extremes. And you see here, this is the excess monsoon of 94, which was an enigma. And that occurred because equino was very, very positive, although ENSO index was negative. And similarly, the drought of 85 occurred because equino was highly negative, although ENSO would have thought that from ENSO we would have thought it should be at least a normal, above normal monsoon. Next. So we have said that there are two modes that we have to figure out, ENSO and equino. Now, lot is known about ENSO and it can even be predicted. I am afraid same is not true about equino, and it is important particularly to understand the positive phase of equino, how it gets generated and its acceptance. If you show the previous slide, okay, never mind. Let's go next. Next, please. No, previous. Where we were, sorry. That's good. So it's very important to understand the genesis of the positive phase of equino, because that is where it can oppose the ENSO phase and actually lead to a different kind of monsoon. Now, what is the prerequisite for understanding genesis of positive phase? The prerequisite is understanding what determines the variability of convection on tropical oceans. Okay, and we all know that the most important parameter is supposed to be SST, sea surface temperature of the ocean beneath the atmosphere in which we are looking at convection. Okay, and this is in fact the basis of the seasonal prediction in the tropics. And in fact, in ENSO there is a very strong relationship between SST and convection over equatorial central Pacific. And this is the modern, you see the correlation is 0.91. This in fact is the modern version of what Berknes showed in 1969. Next. The next slide shows a lot of work has been done on SST rainfall and convection relationship. Pioneering work was by Berknes, who showed that the relationship between Canton Island and SST of the surrounding ocean, which was the equatorial central Pacific. Then we looked at cloudiness intensity, which was the first satellite-derived measure of clouds for the North Indian Ocean, and Graham and Barnett for the entire tropical ocean. And what we got surprisingly is results which were very similar and have been repeated with much more sophisticated measures of convection and SST. Okay, so Now, what are the features of this SST cloudiness relationship? You can see immediately that it's a highly nonlinear relationship, and the propensity of cloudiness is high for large SST, that is SST above a threshold. And that threshold is about 27.5 or 28. And the correlation between cloudiness intensity or OLR and SST is very, very poor in this region where SST threshold is crossed. So here, whether you have convection or not is determined by the dynamics, whether you have convergence or not. The next slide shows you what now we really want to apply whatever we have understood to evolution of SST and OLR of WEIO and EEIO, because those are involved in Equino. Okay, so what you see here is SST of EEIO and SST of WEIO in red, and in general SST EEIO is always higher than SST WEIO. Eastern Indian Ocean is warmer than the Western Indian Ocean equatorial region. Okay, now it so turns out that EEIO SST is determined largely by oceanic dynamics, whereas WEIO SST is determined largely by the fluxes at the surface of the ocean. Now, there are differences, therefore, in what matters for the evolution within the monsoon season of SST EEIO and SST WEIO. I will not get into it, but this is the warm water being advected by Wilkie jet and so on to EEIO. And this is the Sumatra current, Sumatra wind, which leads to upwelling of EEIO and therefore cooling. Okay, so the next slide shows you that actually this is OLR of EEIO and OLR of WEIO here. And here is the upward velocity over the west and over the east. And what you will see is they are pretty close to one another. But all along, just like SST of EEIO is higher than SST of WEIO, OLR of EEIO is lower than OLR of WEIO. That is to say, convection tends to be always more on the east than on the west. Okay, but they are not that far like they are, say, later in the season. So during the monsoon, they are rather close in terms of vertical velocity as well as convection, and they suggest that both the regions seem to be equally favorable for convection. Next slide shows, in fact, that correlation of WEIO and with EEIO is negative. The OLRs are negatively correlated over these regions on monthly and seasonal scales because there is a competition between the two. Okay, and hence if convection over one of them is suppressed by some factor, the convection over the other one gets enhanced. Okay, and this we see on a day-to-day basis from daily satellite data. Now, so it is important to look at not just monthly, but daily. How does the convection vary? And what we find useful is to take a measure of CI, which is the intensity. Now, this is on a daily scale of how many grids in that region have OLR less than 240 and by how much. Okay, this is convective intensity. Next one shows you what happened in 94 and what happened in 85. Now, red here is the convection over EIO, and plotted in blue, but with a minus sign, is the convection over WEIO. Why minus? So that we can see it clearly. That's all. Actually, both represent convection. So what you see is in 94, early on, before the monsoon, actually both west and east were convecting, and east continued to convect a little more until almost June. And then what has happened? East is totally suppressed. Okay, and west is convecting. Okay, so first of all, we notice that this is a case where we would have seen even here that WEIO OLR is less than EEIO OLR, but that doesn't mean that day after day there is no convection of EEIO. It does come now and then. It is just the average is higher propensity for WEIO. Now the opposite case is the 85 drought where it was negative, and what you see is sustained convection over EEIO. WEIO tries to convect but doesn't succeed. So EEIO wins in the competition. So this is how the interaction occurs between these two regions. The next slide shows in fact how the positive phase is sustained, how it is born. It is suggested, this is the actual usual state of affairs with it convecting on EEIO, and then you have winds going towards EEIO, westerly winds. It is believed that intense convection over the bay can suppress the convection over EEIO, and that it does for every IOD event. When that happens, this convection is suppressed. Naturally, convection starts getting enhanced over WEIO. This means the wind switch. Okay, so now you have a positive feedback with the convection and the winds, and this intensifies. This is how the positive phase is generated and sustained. Next. Next. Okay. Now let us go to some concrete examples. Because we want to know, after all, how will the equinu behave in the latter half of monsoon 2019. So first of all, let us look at some examples. And there are two interesting examples. One is 2003, in which equinu got aborted in the middle of the season. Okay, it went on. This is OLR of equinu in OLR of WEIO in 2003, and you can see it is negative here. Okay, but it got aborted around early August. It just crossed over. And what happened at that time? As a matter of fact, it is exactly at that time the SST of WEIO, which cooled because of the intense convection, actually went below the threshold. And at that point, EEIO was warmer and the convection flipped to EEIO, and the whole positive phase got aborted. Notice, on the other hand, and I know you don't have time to see it now, but perhaps later, that 2007 was a case in which, although the SST cooled with the enhancement of convection, it did not go above the threshold in 2007. And although EEIO was warmer, in fact, positive phase was continued in 2007 throughout the summer. Now, this is very interesting. Next one. Next one. Okay. So now the question is, why did the phase abort? And I have already said, in 2003, WEIO cooled below the threshold, and that won't do. So immediately the convection was switched off, and it switched off to EEIO. In 2007, even though there was an intense convection, SST remained above the threshold, and therefore it did not switch over. This is SST of WEIO we are concerned with. Next. Okay. Now, Effie and Francis have shown why is it that in 2007 it was sustained. And I don't have time to get into this. It is just that there was a deepening of isothermal layer of WEIO in 2007 because of Rossby waves and Kelvin waves and so on. And as I said, I have no time to get into mechanism, but it is all written up. So anybody who is interested can look at it. How a westerly wind burst led to deepening of the isothermal layer at WEIO. Okay, and this is what happened in 2007. Next. Next. Okay, so now we come to 2019, where we decided to apply everything we have understood so far. And what we find is the following. See, in 2019, June was a huge deficit of 32%, and July slight excess. Now, this was associated with El Nino, and earlier such an event had occurred in association with El Nino in June was 2014, and 2014 turned out to be a drought of the summer monsoon. So the question was, will 2019 also be a drought, or will it actually, lead to a normal monsoon or an excess monsoon? See, meanwhile, what had happened is warm phase of Enso had weakened a bit. So the important role would have been equinu. So the question was, would a positive phase of equino, which was around, would it continue as it did in 2007 or get aborted as it did in 2003? Next.
You have a couple of minutes left.
Yes, in fact, I'm just going to finish in that. So next, what you see here is 2019, and you see this is EIO convecting and West convecting very well, okay? And this is the point at which we wrote our speculation and our paper. And this is the SST. And you can see that SST had just gone below the threshold around end of July and begun to increase a little bit in early August. This is when we wrote the paper. Next. Next. Okay. So we said, now let us look at the same mechanism that we saw in 2007. And so what happened is we analyzed all the data. Next. Next. Sorry, go back, please. Go back one slide. Okay. See, we analyzed all the data and looked for Rossby waves and Kelvin waves and so on with the help of satellite data and Raman mooring and so on. Okay. And we found that a very similar mechanism to 2007 was operating also in 2019. Okay. So we expect that equino will be sustained. And then we stuck our neck out, next please, and suggested that actually 2019 the convection will continue in WEIO the rest of the season, and we should have a pretty good monsoon because the positive phase of equino would continue. And indeed that is what happened. This is what we had published earlier, and this is what we found. This is what we had seen. And next. Yeah. So I just want to say that it is important to also test out these ideas with the kind of real data now we get for the first time with buoys and everything else, and try and use this to predict the monsoon, which is one of the critical things for us. Thank you.
Thank you, Dr. Gadgil. Let me remind the audience that if they have questions, we will take them at the end of the presentation during the panel discussion, so they can leave them in the chat box. Now we will move on to the next presentation that will be given by Roxy Matthew Cole. Roxy is a climate scientist at the Indian Institute of Tropical Meteorology. He did his PhD in ocean and atmospheric dynamics from Hokkaido University in Japan. Dr. Roxy is currently leading research on climate change to understand how it extends to the rapid warming in the Indo-Pacific region and impact the global rainfall pattern, the monsoon and cyclone, and the marine ecosystems. He is a chair of the CLIVAR Indian Ocean Region Panel and a lead author of the IPCC report. He actively collaborated with citizen science network, local government, and media to bring science to the society. Roxy is among the list of the top 2% scientists ranked by Stanford University. He was awarded the Kaliv Fellowship in 2015 and the NRC Senior Research Associateship in 2018 by the US National Academy of Science. The Indian Meteorology Society felicitated him with the Young Scientist Award in 2016 for his research on the change in the monsoon. So Roxy, the floor is yours, and you have 20 minutes.
Thanks, Mary, for a warm welcome. I was hoping that we would have an in-person meeting this time. In fact, I had booked my accommodation twice to come to Goa and have, along with my students, drive down from Pune to Goa and interact with you all. But unfortunately, it's all virtual. But here I am talking about the Indian Ocean, the need for observations, sustained observations in the Indian Ocean. INDOS means Indian Ocean Observing System. Now, Mike, in his first talk, and Sulojana entered with saying to observe changes in the monsoon, in the Indian Ocean, we need long-term data that can go into forecasts and also make us understand the long-term changes that's happening in the Indian Ocean. So this is work that has a history of several years, and this is the talk is based on a review on the Indian Ocean Observing System. I have put in a few names here: Lisa Beale, Jerome Viola, Juliet Hermes, Jean Lee, who are part of the Indian Ocean region panel. But this was a massive effort lasting for 4 years or more. I will get to the numbers later, but there are some core findings from this, and I have listed out straight away here that the Indian Ocean is warming at a rapid pace, presenting new weather and climate challenges, particularly in terms of monsoon, extreme weather events to South Asia, and the Indian Ocean region, which asks or calls for a redesign of the observing systems to address these challenges. And for that, we need improved observations and forecasts that require regional partnerships and data sharing. So here in this slide, we can see some of the major Indian Ocean features. And you see this warm reddish colors over here. That's the Wampo region, which sustains enhanced convection over the Indian Ocean region, and it oscillates between the North Indian Ocean and the Equatorial Indian Ocean depending on the season, and supports the monsoon over the region. And it's not a one-way relationship. We have ocean atmosphere interaction throughout, and we have the monsoon winds acting in summer and winter in different directions. And you can see the response in the ocean also. You can see most of these arrows depicted here are in two directions based on the seasonal reversal of the monsoon winds. The upwelling currents are in two directions, the monsoon currents, the Ritchie jets. So there are a lot of seasonal variability in this Indian Ocean region. So it's basically a monsoon-induced climatology. But then there are long-term or decadal scale variability as well. You can see the Indonesian through flow. You can see the cross-equatorial cells, subtropical cells, which are meridional circulation that Mike was talking about. And then there are many other currents and subduction, many activities dynamics going on in the Indian Ocean, along with biogeochemical responses as well. You can see there the Arabian Sea and the Bay of Bengal are one of the some of the largest oxygen minimum zones affecting productivity as well. So many of these features we have understood due to sustained oceanic observations during the last couple of decades. Now there are emerging challenges that are changing each and every element of this, particularly due to anthropogenic climate change. And now in the title itself, we saw that Indian Ocean is warming at a rapid pace. And this is particularly highlighted by the recent 6th assessment report of IPCC. I have copy-pasted the snippet of that report, which says that since the 1950s, the fastest surface warming has occurred in the Indian Ocean. And you can see the observed trend during the last few decades since 1950s. The temperatures are up to 1.2 degrees Celsius, 1.3 degrees Celsius in this Indian Ocean region, which are quite high compared to the temperatures observed over the land or the global mean, which is around global surface mean temperatures is around 1.1 degrees Celsius, and global ocean surface warming is around 0.8 to 0.9 degrees Celsius. So that's quite large, but even that is dwarfed if you look at the projections. So the black line here shows the historical, and the yellow line shows the observed SST changes during the last century or more. And we can see that this is dwarfed by the projected changes. So if the observed change is around 1.2 degrees Celsius per century, the projected changes on a high road with the current emission scenarios, which we have not contained, is about 3.8 degrees Celsius per century. Now, mind you, this is the average over the entire basin. We have a basin-wide warming over the Indian Ocean. Most of the changes that we see until now is because of these observed changes. So what we could have due to this projected changes is unimaginable. I'm looking at some of the emerging changes that is connected to the society. You would hear more about monsoons in the next talk by Krishnan, but one of the salient changes cutting across the Indian Ocean region are the monsoon floods due to extreme heavy rainfall events, which are going to continue into the future as well. So South Asia, East Asia, and many other regions around the Indian Ocean rim are already seeing monsoon floods, and some regions are affected by droughts as well. And then we have increasing cyclones, particularly over the Arabian Sea region, or changing cyclone characteristics like rapid intensification. And connected with that, storm surges, heat waves over the Indo-Pak region. We have heat waves over the ocean as well. In fact, there is a talk today afternoon on marine heat waves from one of my students. And as a response to increased surface temperatures and stratification, we have changes in the marine phytoplankton. So all these changes that you see here affects the food and water security of the Indian Ocean region. And we are yet to understand and quantify most of these changes. And an overarching change for all these regions, especially coastal cities, is the sea level rise. We already see islands disappearing and sinking in the Indian Ocean region, particularly in the East Indian Ocean region and in the Bay of Bengal. Now, what happens here in the Indian Ocean do not stay here in the Indian Ocean. The impacts are beyond. We have seen studies showing that it impacts the circulations, it impacts the variability in the Pacific and the Atlantic. It even impacts the meridional overturning circulation, which means there are climate implications to this too. Now, I am highlighting some of the major extreme weather events. One is the changing status of cyclones due to Indian Ocean warming. Now, if you compare to other regions like the Pacific, especially Northwest Pacific and Southern Hemisphere, the Indian Ocean have only 6% cyclones, but accounts for, historically, in the recent period it has changed, historically it has accounted for 80% of fatalities, and we still see that a lot of fatalities happening in this region. Our cyclone forecasts have improved, but still the damage is high because the frequency, intensity, and duration of cyclones have increased in the recent period. And one of the aspects that has changed is the rapid intensification of cyclones. Like these two cyclones, especially cyclone Amphan, intensified from a category 1 to category 5 cyclone in 18 hours. Now, these cyclones also, in the last 2 years, there were back-to-back cyclones in the pre-monsoon period, very close to the monsoon onset, interacting with the monsoon and changing the dynamics of the monsoon. And we see that extreme high temperatures, showing characteristics of a marine heat wave. So these are the normal temperatures. You can look at the color scales. It ranges from 28 to 31 degrees Celsius. But during these marine heat waves prior to the cyclone, the temperatures are so high, it reached up to 32, 33 degrees Celsius. Temperatures that also could result in coral bleaching. Yeah, but we do not have very accurate measurements of these ocean and atmospheric factors. In fact, even our wind observations of cyclones are patchy. I will show. I think I have a slide on that. And we do not have subsurface data, ocean subsurface data at very high resolution to study or understand and quantify these marine heat waves. Now, the same marine heat waves that can intensify a cyclone also lead to coral bleaching, because corals have mucous membranes which act as a shield and gives the color. Warm temperatures bleach it away, as you see in this picture. This from a documentary, Chasing Coral from Netflix. So you can see there are multiple events either cascading and compound events, and we need to start monitoring these kind of events and quantify these events which are happening in the I talked about gaps in observations, especially with respect to temperature. Now, this is a marine heat wave prior to cyclone Amphan. You can see the temperatures here. The blue line shows the mean temperatures, and the green line shows the 90th percentile. So what falls above the 90th percentile is a marine heat wave. So these are temperatures well up to 2-3 degrees or more above the mean temperatures, right? Extremely high temperatures. And you can see when cyclone Amphan occurred, and then you have a cooling. Now, the buoys from the Ministry of Earth Sciences under NIOT and IIOSC, they also measured very high temperatures. In fact, so here you have from the satellites temperatures between 31-32 degrees Celsius, but these buoys shows temperatures up to 34 degrees Celsius and then cooling after the cyclone. Now, are these dependable temperatures? Are these errors due to the platforms that we have there? We don't know, which means we need validation of this with multiple buoys. We need more high resolution observations in the Indian Ocean. Now, there are other gaps in the Indian Ocean also. Mike was talking about the Somali upwelling. Now, if you look at the Somali upwelling, that is one of the regions where we have a lot of fluxes, heat fluxes. The mean heat fluxes, this from 6 products available, shows it's about 60 watts per meter square. But the uncertainty in this region is also up to almost same values. And the entire equatorial and the Western Indian Ocean and most of the Northern Indian Ocean and also even the Agulhas region, the uncertainty in the heat fluxes. Yesterday, one of IITM students, Ushnanshu Datta, also showed there was a lot of disparity between flux observations. And one of the reasons is that we do not have flux observations, in situ flux observations at many of these locations. So this also prevents us from quantifying compound events, where sea level rise, storm surge, heavy rains, and flooded river can overlap, or heat waves and droughts can overlap. We need to have a quantified understanding of compound events in this Indian Ocean region. And the recent IPCC report shows that these events are increasing. So how do we monitor and forecast these changes? We do that with the help of satellites, of course. You can see satellites here. But at the same time, we need in situ observations that can measure not only the surface data, but also the subsurface data, because many of these high resolution diurnal variability is important for intraseasonal variability that Sulochana was talking about, the monsoon intraseasonal oscillation, the Madden-Julian oscillations. There is a talk later today. I am giving that talk on how the Indo-Pacific warming is changing the Madden-Julian oscillation and region rainfall. So all these observations feed back to or are given as inputs to forecast for agriculture, farming, water resource management, fisheries, marine transportations. We call them these sustained observations as the Indian Ocean Observing System. You can see there is a full report of 25 chapters over 3 to 4 years and 136 actionable recommendations, which means there are a lot of gaps which prevents us from understanding the changes and variability in the Indian Ocean. And we had several workshops brainstorming on the requirements, and I am putting up some key or core recommendations out here. The observing systems consist of Argo, within Argo itself, BioArgo, Deep Argo, Rama moorings, which Mike was talking about, XPT lines, sustained XPT lines, tide gauges, surface drifters, GOSHIP, and boundary current arrays like for the Agulhas and all. We don't have boundary current arrays for the Somali and all. So core recommendations are chemical, biological, and ecosystem measurements alongside physical parameters are required. Now, most of the current measurements focus on the physical parameters, but we need to expand that. We need to expand into the Western Indian Ocean and the Arabian Sea to improve current understanding of the monsoon circulation, because a lot of biases in the data are coming from here. We need better resolved upper ocean processes to improve, so not only surface but also subsurface, to improve understanding of air-sea coupling and yield subseasonal to seasonal variation. It's quite important for monsoon forecasts. Expansion into key coastal regions. exclusive economic zones, and a deep ocean to better constrain the basin-wide energy budget. We know that the Indian Ocean warming is happening, but if you look depth-wise, we still do not have accurate quantified estimates of the basin-wide energy budget. Now, this requires regional partnerships. One country alone or two countries alone cannot observe the entire Indian Ocean. There is a huge need for increased investment and stronger partnerships within India, Indian Ocean rim countries, and also end users. And this also calls for improved data sharing and commitments to best practices. Sometimes some countries collect data, but it's not shared for public research. Now, this is a very nice, this photo is a very nice example of regional partnerships. This is a ship, the Sagar Kanya. I also took part on a cruise in this ship, Sagar Kanya from the Ministry of Earth Sciences. And the buoy is from the Rama moorings from NOAA, a beautiful India-US partnership. So we need more of such partnerships where which can scale up our observations in the Indian Ocean. And recently, even the Indian buoy networks called the Omni moorings were provided for data sharing to the public, and a framework, a common framework with the Rama moorings is coming up. But we have still a way forward. There are moorings and hydrographic data collected along the coastal regions, which are quite important for monsoons and western boundary current and the boundary current processes. So we need access to hydrographic data in the exclusive economic zones. We need capacity building along the Indian Ocean rim countries. So these are some of the major recommendations from Indus, the Indus review. And another important thing is that we cannot live without satellites, but even satellite estimates are patchy. Even the cyclones that we see, we do not see the full picture. There is a WMO requirement that says that we need at least 3 scatterometers in coordinated orbits for 90% coverage. But at present, we are unable to cover the Indian Ocean fully. We have only 60% coverage with 2 satellites at the time. And also, we do not have coverage. These are the timings of the satellites. We do not cover the satellites. We do not cover the Indian Ocean during the early hours, which prevents us from understanding the evolution of cyclones itself. We cannot measure the maximum sustained winds of cyclones at all the times. So this kind of, but we need diurnal sampling to understand this, the trigger, the genesis, the evolution of cyclones, and even the monsoon and intra-seasonal and seasonal timescales, and also to forecast them. There are other opportunities for Indian Ocean observations as well, which are not part of Indus, but which could be. We need observations for the PCO2, and this can be easily sustained along with existing observations, existing Rama Omni moorings, and also the ship tracks. We can have interactions with the private sectors. There is a proposal from Jim Kosopoulos. He might be presenting in a later talk for including atmospheric instrumentation suite. It's a next generation smart atmospheric observatory for deployment over world oceans. So together with collective action, we can observe the Indian Ocean. And that would make it one of the best observed ocean basins. But mind you, it's also the fastest changing ocean in the tropics. So from, if you look at 1990s, Indian Ocean was poorly observed. The Pacific, we already had some of the observatory system there, but it was poorly observed. Then came the Indus, the first set of Indus observations. We can see the original design and current status. But there were several gaps. Many of these open boxes are gaps. So if we can fill those gaps and sustain these observations, we could understand the decadal and long-term changes in the Indian Ocean, and also improve the seasonal, intra-seasonal, and long-term forecast for the Indian Ocean region, from Africa to Asia to Australia. So that's it. Thanks for listening to this talk. All this work stems from the coordinated effort from the Indian Ocean Network, the IPCC team, some of my lab members. Also, we see opportunity to work this out, these observations through the UN Decade of Ocean. So the report is out there. You can just Google for INDUS 2, 25 chapters. We also have a BAMS synthesis out of this. Thanks to all.
Thank you, Roxy, for this nice presentation that already sets a scene for the panel discussion that we'll have later in this session. Now I would like to call our next speaker, Dr. Krishnan. He is a senior scientist and executive director of the Center of Climate Change Research, working in the field of climate modeling and analysis at the Indian Institute of Tropical Meteorology. He did his PhD from the University of Pune. His research is focused on climate modeling with a special focus on the dynamic and variability of Asian monsoon and global climate change, as well as impact of monsoon on hydrological cycle. Dr. Krishnan is a fellow of the Indian National Science of Academy and Indian Academy of Science and Indian Meteorology Society. He is also a member of the Joint Scientific Committee of WMO-WCRP, and he has been coordinating as a lead author the 6th assessment report of IPCC Working Group 1. Dr. Krishnan has received several awards, including Frontier Outstanding Research Award of MOIS, National Award. So Dr. Krishnan will give a presentation on the monsoon hydrological cycle response to global climate change and give key messages from the IPCC Assessment Report 6. Dr. Krishnan, the floor is yours.
Yeah, thank you very much, Mary. Good morning to all of you, and thank you, IIOSC, for this opportunity. Yeah, just share my slides. Just a minute. Is my slide visible?
Not yet.
Okay. Yeah. So good morning to all of you. Today I'll be talking about the monsoon hydrological cycle response to global climate change. Basically, the key messages from the IPCC are six.
We can't see your slides. We can't see your slides.
Oh, you cannot see it? Okay. Yeah. Just a minute. Sorry. Is it visible now?
No.
No.
At least not for me.
Wait a minute.
Yeah, Dr. Krishnan, I think you need to share your screen.
Okay. Yeah. Just a minute. Share.
It's coming now.
Is it okay now?
It's fine. You can start.
Okay. Yeah. Yeah. Thank you very much. Today I'll be talking about the monsoon hydrological cycle response to global climate change. Basically, some of the key messages from the IPCC AR6. So the recent AR6 report that came out last year, it has provided very convincing, compelling evidence of the human influence on the warming of the climate at a rate that is unprecedented in the last 2000 years. And so, of course, the warming is very clear in the last 2000 years, and this is due to the human influence. And if we look at the multi-century period, this has been the warmest multi-century period during the for more than 100,000 years. And there is also a very strong human attribution by the AR6 models, the CMIP6 models. So the warming trend that we are seeing since 1850 is largely explained, can be attributed to the influence of human activities and cannot be explained only by natural forcings, such as the solar or volcanic forcing. And we also see episodes of cooling. These are typically associated with the major volcanic eruptions, the Pinatubo and the El Chichon and so on. But by and large, the warming since at least the mid-20th century, what we are seeing is largely attributable to the effect of the greenhouse gases primarily. And there are also, in addition to greenhouse gases, there are other drivers that have influenced the global climate change. And if we had only, this is all from the CMIP6 models that contributed to the ER6. If we had only well-mixed greenhouse gases, the warming would have been around 1.5 degrees. The observed warming 2010 to 2019 relative to 1850 to 1900 is about 1.1. And this has been basically offset by other drivers, particularly the anthropogenic aerosols coming in the form of sulfur dioxide and organic carbon and other non-greenhouse gases. So we have to keep in mind that the changes, temperature change is not only by greenhouse gases, but also due to other forcings, especially the aerosols, which have masked the effect of the greenhouse gases. And this is particularly important for understanding the hydrological cycle and the monsoonal changes. And in the future, except the very low emission scenario, the SSP 119, where we are able to limit the warming by end of this 21st century to below 2 degrees. In all the scenarios, we are exceeding 2-degree warming. And even the middle of the road, the SSP 245 is a kind of the middle of the road scenario where the warming is projected to be close to 2.7 degrees. And the high emission scenarios, the warming levels are much higher. And in the next 20 years, we will cross the 1.5 degree warming level, 1.5 degree warming compared to the pre-industrial period. And so this is very compelling evidence. And we are seeing these effects not only in the surface temperature over land, but also in terms of the ocean heat content. So the human influence is clearly coming out, and the surface air temperature increase even on a continental basis, whether it's North America or Europe and different parts of the world. We see the influence of the human influence affecting the warming that we have seen. And with regard to the precipitation changes, when we look at the global precipitation, there has been an increasing trend in the precipitation during the second half of the 20th century, since the mid-20th century. And this is attributable again on a global scale to the human influence, and particularly in the high latitudes and the high and the mid latitude, the increase of observed precipitation is attributable due to the human influence. This is all coming from the ER6. And due to the warming, we are also seeing a very large reduction in the decrease of the Arctic sea ice. And especially after the 1990s, the depletion has been very, very pronounced. And this is attributable again to the influence of the global climate change. And the models in the Antarctic, the decrease of the ice cover has been much reduced. And actually the observed changes, we started seeing the decrease since 2016 or so in the observations, but the models seem to project an increased reduction. So there are deep uncertainties when we talk about the Antarctic sea ice. I'll not be able to discuss that in this talk. So, and much of the warming dominates the energy inventory change, accounting for 91% of the observed energy increase. So the ocean warming has been predominant, and it's not only the sea surface temperature, also the deeper oceans. So you can go in the subsurface up to 700 meters and even below. So the ocean warming has substantially increased during the historical period. This is from 1971 to 2018. And these are the ocean heat content trends. This is the surface to 700 meter depth. You can see warming, the increase in the ocean heat content in many parts of the global oceans. And when you go to the deeper layers, especially the 0 to 2000 meters depth, you can see pronounced increase in the ocean heat content, especially in the Indian Ocean. Whereas the other, especially the North Pacific and the North Atlantic, the changes are more, they're spatially varying, and some regions have also experienced a decrease. And these are associated with multi-decadal changes in the circulation patterns, in the ocean circulation patterns. But there has been a rapid warming of the Indian Ocean. This was brought out in Roxy stock and also McFadden stock. So there's a very substantial increase in the ocean heat content, particularly in the Indian Ocean. And they have also the increase of due to the thermal expansion and also due to the melting of the glaciers and the ice sheet, there has been an increase in the global sea level and also different regions of the oceans. And there's a very strong attribution to this in the IPCC AR6. And so this is basically the sea level increase due to the thermal expansion. So there's a clear attribution which says that combining the attributable contributions from glaciers, ice sheets, surface mass balance, and thermal expansion, it is very likely that human influence was the main driver of the observed global mean sea level rise since at least 1970. And there's also a very strong regional attribution in the AR6. So with every increment of global warming, changes get larger in regional mean temperature, precipitation, and soil moisture. So this is the observed change, what we are seeing per 1 degree global warming. And this is what is simulated by all the CMIP6 models. This is for the observed period. And so at a 1.5 degree warming, global warming, that which we expect in the next 15 years, you can see very pronounced warming in the high latitudes, in the polar regions, and also many parts of you can see the global warming signature. And the similar pattern is amplified at 2 degree global warming and 4 degree global warming levels. And in the future, with increased warming, we see precipitation enhancement, particularly in the mid latitude and the high latitude, and also the monsoon regions, many monsoon regions for South and Southeast Asia, the West Africa, and the East Asian monsoons. And you can see the dry areas are mostly in the subtropical areas where there is more descent. So it's like the wet gets wetter and dry gets dry paradigm. So the subtropical areas are projected to increase. They are expected to show more decrease in the precipitation. So the aridity in the subtropics will increase. The Mediterranean and other areas and parts of southwestern Australia. And so with warming, a typical signature is the wet gets wetter and the dry gets drier kind of paradigm we see. And I was involved with this chapter on water cycle changes as a coordinating lead author. So I will just present some of the monsoonal changes and monsoon is one of the important topics of the water cycle change. And so this chapter has a very robust assessment of different components of the global water cycle. And if you look at it discusses about the stores, the water stores in different components of the global water cycle. We see that more than 96% of the water is in the oceans, seas and bays, and about something close to 3.6% of the water is available in saline groundwater and surface fresh water. So basically what is really usable for humanity, for the mankind, is only about 1.8%. And so water is really a very, very scarce commodity. And there is also an assessment of the water fluxes, how they are exchanged among the different components of the climate system. The ocean is the main source of the evaporation, the flux of water, and much of it is whatever is evaporated from the oceans is precipitated over the oceans, and a significant part of it is transported to the land and contributes to the precipitation over land. And this is particularly relevant when we are talking about the monsoon and the South Asian monsoon. This is just a schematic of the South Asian monsoon, where there is a strong coupling between the circulation, the monsoon large-scale circulation, and the rainfall. So due to the setting up of the thermal contrast between the land and ocean, it is required to set up a monsoon type of circulation, But once this circulation is established, there is a feedback between the circulation and the latent heat of release. So when the water vapor condenses to form clouds, it releases huge amounts of latent heating, and which can drive and maintain the circulation on a continental scale over the South Asian region. And of course, we do see year-to-year variations in the monsoon rainfall, and they can be affected by the internal dynamics of the monsoon system and also various modes of climate variability like ENSO, IOD, and Equino, and several drivers, as well as external drivers. When I say external drivers, we are talking about human influence or volcanic eruptions, natural forcings like volcanic eruptions, and so on. So this is a very simplistic picture. Now in the AR6, we are having an assessment of both the global and the regional monsoons. The black contour in this picture shows this is the domain of the global monsoon, which is defined as the area where the local summer minus winter precipitation exceeds 2.5 millimeter per day. And this definition was used in the AR5. Now in the AR6, we are also talking about regional monsoons, which are defined based on published literature and expert judgment from the different regions, and also accounting for the fact that the climatological summer monsoon season varies across individual regions. So we have the South and Southeast Asian monsoon region shown by this pink color, and this purple region is the East Asian monsoon. We have a Australia and Maritime Continent monsoon shown by the yellow color, and we have the West African monsoon. And in this AR5, the South Africa was called as a monsoon region, but in the AR6, we don't call it as a monsoon region. There are strong seasonal cycle in the precipitation changes over South Africa and also over equatorial America. So we don't classify that as regional monsoon in the AR6. And these areas are shown by dots, the stipplings, and we have the North American monsoon and the South American monsoon. The main assessment is the global land monsoon precipitation. This is for the observed change, decreased from 50s to the 80s, partly due to anthropogenic aerosols, but has increased since then after the 80s in response to greenhouse gas forcing and large-scale multi-decadal variability. This comes with a medium confidence. During the 21st century, global land monsoon precipitation is projected to increase in response to greenhouse gas warming in all time horizons and scenarios. This is a high confidence statement, and in the long term, global monsoon rainfall will feature a robust north-south asymmetry characterized by greater increase in the northern hemisphere. So the northern hemispheric monsoon regions are going to get more precipitation than the southern hemisphere, and an east-west asymmetry characterized by enhanced Asian and African monsoons. So the Asian and African monsoons are projected to increase, and a weakened North American monsoon. This is the simple summary. And we are able to assess the fingerprints of both the green. As I said, there are multiple drivers, anthropogenic drivers like the greenhouse gases and the aerosols. So the fingerprints of these, both the GHG and the aerosols, both on the temperature and the precipitation changes have been assessed. This is based on the CMIP-5 models by Bonfils et al. You can see the temperature increase due to the greenhouse gas. It is kind of a global signature with strong loadings over the polar and the high latitudes. When we see the aerosol fingerprint on temperature, you can see that much of the decrease in temperature due to the aerosol is over the continents of America and Europe and Asia. And you see a strong interhemispheric asymmetry in the temperature fingerprint. And we also know that we have understood that if you relatively is one of the hemispheres is cooled due to, let us say, anthropogenic aerosols or volcanic aerosols relative to the other hemisphere, the ITCZ generally tends to shift, and this dynamics is being understood nowadays. And when we look at the precipitation fingerprint of aerosols, we see that you can see a decrease of precipitation particularly in the northern hemisphere, many monsoon regions of South and East Asia, and also the West African region, and an increase in the precipitation to the south of the equator. Whereas when you look at the precipitation fingerprint of greenhouse gas, you see strong increase in the precipitation in the middle and high latitudes and some of the monsoon regions with pronounced subtropical drying. And both the signatures of the air's temperature and precipitation change, we also see them in terms of the heredity fingerprints. So, and as I said, now we have the observations of the solar shortwave radiation changes, what is known as the Global Energy Balance System. This is known as the JEBA data set for the Northern Hemisphere. They have systematically measured how the solar radiation has been dimming in the Northern Hemisphere. And due to the influence of the aerosols, they reduce the incoming shortwave radiation at the surface. And so we can see that much of the Northern Hemispheric region since the 60s, there was a pronounced decrease in the radiation until the 90s, and there is thereafter some recovery, largely due to the regulation of the aerosol emission norms, particularly over North America and Europe. There has been a recovery in this dimming. This pattern we do see, and also due to the subsequent increase in the greenhouse gases. The greenhouse gas having a longer lifetime, and they have been steadily increasing over time. And so what we are seeing is there has been a reduction in the aerosol forcing, particularly over the impact of that we see especially for the West African monsoon region. And so the precipitation, the Northern Hemispheric land precipitation, this is defined by the Polson et al. Paper. This is the region of the Northern Hemispheric land monsoon. Precipitation decreased in this region from the 60s up to the early 90s, and then due to the reduction in the aerosol forcing, and also due to the increase of the greenhouse gases, and also the effect of decadal variability, there has been a recovery of the precipitation after the 90s. And this particularly we see over the West Africa. I'll be talking about this. The CMIP6 models are able to capture this contrasting effects of the greenhouse gas and aerosol forcings, although the magnitude of the variability, the interdecadal variability, the models are not able to capture. This is something we have to keep in mind. So when we look at the trend and change in the monsoon precipitation for different regions, this is for the South and Southeast Asia. The observed precipitation we have shown from 3 different data sets, the Aphrodite, CRU, and the GPCC. And this is for the period 1951 to 2014. We do see a decrease in the precipitation. The magnitude varies depending on the data set. And when we look at the CMIP6 models, we have the natural experiment where there is no anthropogenic forcing, that is the blue whiskers. And then the black is the all forcing experiment. This is the only if you have the greenhouse gas, this is shown by the red box whisker, and the green is only the aerosol forcing. So the contrasting signatures of the monsoon precipitation change between the aerosol and the greenhouse gas is very clearly seen in the over South Asia and also over the East Asian region. And we have also shown the all forcing experiment and the observed variation time series itself. The top panel is only the trends from the multi-models. So the models are able to bring out the contrasting influence of the different forces. And in the future, with reductions in the aerosol forcing and continuation of the global warming, we see that the monsoon precipitation over South Asia and East Asia is projected to increase, particularly in the middle and the long term. These were for different scenarios. When I say the near term is 2021 to 2040, midterm is 2041 to 2060, and long term is 2081 to 2100. And we have 3 different scenarios: the low emission, that is SSP 126, the yellow is the SSP 245, the middle of the road, and this is the high emission scenario 585. So precipitation, especially in the middle and long term, you can see that it is projected to very clearly increase in the middle and long term. This is one of the clear messages. In the near term, especially, we are seeing the influence of decadal variability. When we come to the West African monsoon, this is an important point. We do see from the 60s, we see up to the 80s, there was a substantial reduction in the monsoon. The magnitude of decline in precipitation over West Africa was substantial. Thereafter, after the 90s, there was a increase, there was a kind of recovery. And So we see a large interdecadal variability also. Especially in the 60s and 70s, Sahel region, West African Sahel, used to witness decades of droughts. And that situation, there's a recovery after the 90s. And these signals, the models are able to capture to some extent, although the magnitude of the decadal variability, the CMIP6 models are having limitation. And in the future, the West African monsoon, especially in the middle and long term, it is projected to increase. So why I particularly wanted to highlight this inability of the CMIP6 model to capture the decadal variability is it has strong links to the Indian Ocean. The Indian Ocean warming studies have shown that they have a significant influence on the West African monsoon precipitation. And with continued warming, the warming that we are seeing and which is also projected to increase in the coming decades may have implications for the decadal timescale variations, particularly for the West African monsoon. And for the Indian monsoon in terms of the extreme precipitation, because with every 1 degree warming, we are going to increase the water vapor in the atmosphere by 7%. So the extreme precipitation is going to increase. So these are some of the key messages. The human-induced climate change is already affecting many weather and climate extremes in every region across the globe. And evidence of observed changes in extremes such as heat waves, heavy precipitation, droughts, and tropical cyclones, and in particular, their attribution to human influence has strengthened since AR5. And this is one of the statements on the global land monsoon precipitation, which decreased from the 50s to the 80s. They are partly attributed to the human-caused Northern Hemisphere aerosol emissions, but increases since then have resulted from rising GHG concentrations and decadal to multi-decadal internal variability. This is a medium confidence statement. Over South Asia, East Asia, and West Africa, increases in monsoon precipitation due to warming from greenhouse gas emissions were counteracted by decreases in monsoon precipitation due to cooling from human-caused aerosol emissions over the 20th century. This is a high confidence statement. Increases in West African monsoon precipitation since the 80s are partly due to growing influence of greenhouse gases and reductions in the cooling effect of human-caused aerosol emissions over Europe and North America. Medium confidence. This is for the future. Continued global warming is projected to further intensify the global water cycle, including its variability. It is not only the water cycle will intensify, also it's going to become more variable, and global monsoon precipitation and severity of the wet and dry events is going to increase. So there is strengthened evidence since AR5 that the global water cycle will continue to intensify as global temperatures rise. High confidence, with precipitation and surface water flows projected to become more variable over most land regions with seasons. The high confidence, and from year to year, medium confidence. And precipitation is projected to increase over high latitudes, the equatorial Pacific, and parts of the monsoon regions, but decrease over parts of the subtropics and limited areas in the tropics in the SSP 245. This is a kind of middle of the road scenario, and also the SSP 370 and 585. These are kind of high emission scenarios. And lastly, a warmer climate will intensify very wet and very dry weather and climate events and seasons with implications for flooding or drought. High confidence. But the location and frequency of these events depend on projected changes in the regional atmospheric circulation. So the changes in the circulation can have implications on the location and frequency, including monsoons and the mid-latitude storm tracks. Monsoon precipitation is projected to increase in the mid and long term at global scale, particularly over South and Southeast Asia, East Asia, and West Africa, apart from the far West Sahel. High confidence. So with this, I come to the end of my talk. Thanks for your kind attention. Thank you.
Thank you, Dr. Krishnan,
Yeah.
for your nice presentation of the latest result of the 6th research assessment of IPCC. We'd like move on. We will move on now to the final part of our session, which is the panel discussion. And before we start reflecting on the 2 questions that have been addressed by the organizer, I would like to check in the chat box, and I see that there are some questions already. So we'll start with the question. 2 of them are addressed to Mike, and these are questions from Dr. Satish Shenoy. So, Mike, don't you think that the volume transport based on wind stress could be the most reliable in view of the validation of the ADCP current of cross-equatorial flow? That's the first question. Are you with us, Michael?
Yes.
Yes. Okay.
Can you hear me? Yeah.
Yes.
Yeah. That's a great question, Satish. Actually, I think for the cross-equatorial flow, I think the wind stress is a solid estimate of that, just because of the fact that we can estimate the transports from the observations, at least at one meridian. I mean, it's one thing to validate the winds, which often is done against moorings or whatever. But then when you start taking gradients like you take with a wind stress curl, any small errors can be amplified. So the fact that the wind stress curl is a gradient calculation and the transports that we estimate from that match well with those from the moorings gives me actually a lot of confidence in the wind stress curl calculation along the equator. For the other regions, I guess it's harder to know because it is a calculation that's sensitive to how you compute the gradients in the winds to get the curl. And it is a calculation that is sensitive to the scale over which you compute those gradients. And, it becomes a delicate signal to noise problem. So, in the other region where we looked at it in the Seychelles-Chagos thermocline ridge region, I'm not sure which is the best estimate actually, because they all require some level of assumption and they all have different kinds of noise associated with them. And that's why doing it with several different approaches helps us, I think, to home in on, what the right answer might be. Ideally, what we'd like to do is have an ocean analysis that's well calibrated with a long history of observations that were more or less consistent over time, but we'll never have that. So, I mean, there is a problem in doing these comparisons. That's in part to address your second question. I mean, comparing, it's hard to compare some of the modern measurements that we're making, with drifter estimated upwelling velocities from some of the ones that Fritz Schopp did, which were based on cruises. He had a series of cruises in the Somali Current region, and from those he pieced together a seasonal cycle and a mean. We're not doing those cruises today, so we can't repeat the calculation in exactly the same way. So there are these residual uncertainties in comparing those old data to the newer data. And the way to do this consistently is, as I say, to have a long reanalysis that is consistent across time, from which you can compare, in which all the data that we have has been assimilated into that. And that would give us the most complete picture, and it would be the most, we would have the most confidence by computing the differences in earlier and later times from such a reanalysis product. So ultimately, I think it's reanalyses that are well calibrated against good observations to do the change calculations.
Okay, so since you answered the second question, then we will move to the next question that I think is for Roxy. How much perfectly can we believe remote sensing temperature data?
The remote sense data, I mean, we have a huge coverage now and the accuracy is quite high. And the errors could be, compared to in situ, could be 0.1, 0.2 degrees Celsius, that's all. But the point here would be that the satellites do not measure the temperatures beyond the skin or the surface. So many of these, quantifying many of these events like marine heat waves, which go below the surface to the subsurface, requires in situ or on-site data collection using in situ platforms. Not only that, these measurements of temperatures, subsurface temperatures, are quite important for estimating the tropical cyclone heat potential and other input data that are provided for the models to forecast these extreme weather events on short time scales, and also the monsoon on longer time scales. So that's the key message. Thank you.
Thank you, Roxy. I have another question, I think to Mike, back to Mike, from Ramadan Yadav. What is the cyclicity of SCTR, and how does and what are its association with ENSO and IOD?
Okay, there's a lot of questions there. There is definitely a seasonal cycle to the SCTR. I actually had a plot of that, which I took out of the presentation just because of time limitations. It is strongly influenced by the seasonal migrations of the intertropical convergence zone. So it's most, the upwelling is strongest in the early part of the calendar year, January, February, March, when the IPCC is south of the equator and the curl is strong in that region. And then it weakens in the boreal summer as the IPCC moves north and the rain concentrates over the Asian continent. In terms of interannual variability, it's influenced by both ENSO and the IOD. And so, for example, when there's a positive IOD, the sea level rises in the Western Indian Ocean and the thermocline is pushed down. So there's a clear modulation associated with the IOD, and the reverse happens with a negative IOD. And likewise with ENSO. And so when there's a strong ENSO event, sea level will rise in the Western Pacific also because of Rossby wave propagation. And so it has both a strong seasonal and interannual variability.
Okay, and there is another question on the SCTR. Does it prevent intermediate water to reach the Bay of Bengal from southern sources?
Yes, I didn't have a chance to comment on that either, but that thermocline ridge is very intense and it extends almost all the way across the basin. And it's effectively a potential vorticity barrier to interior pathways for subtropical water subducted into the thermocline from making a transit across the equator in the interior basin. It all has to go through the western boundary, essentially, because it's in order to conserve potential vorticity, the water parcels cannot penetrate that really strong ridge. And it's basically because the vertical stratification intensifies in that region. So you have it's a vortex stretching argument. So yeah, it's a very interesting dynamical block to north-south transport from the subtropical Southern Ocean to the equator in the interior.
Okay, I don't see any other question in the chat box.
There is a question from Srinivas.
Yes, just coming. Let me see. Does one of the chat, this is for you, Roxy, right?
Yeah.
Okay, so yes, one of the challenges in long-term sustenance of ocean observing network is the perception that to primarily address research application. Do you think it might be useful to generate clear use cases regarding the use of data from ocean observing network for ocean operational application services similar to service weather observations? And is that something that IIOSC is considering?
Yeah, thanks, Srinivas. I agree with you totally. There could be a perception that ocean observing networks are just for research applications, but we know clearly, especially over the Indian Ocean, and not only Indian Ocean, for the other ocean basins as well, this connects well with the weather and climate forecasting that is directly applicable for the society. And in fact, IIIOSC had recently done an economic impact assessment of ocean observing networks and their applications. So, which has clearly shown how much these ocean observations are directly connected to society in terms of disaster management and all. So And you asked about how the Indian Ocean Panel can be part of it. In fact, Indian Ocean Panel is under the World Climate Research Program Project CLIVAR, and there is a restructuring going on, which highlights or tries to bring the society part and bridge that disconnect with science, between science and society. And this is where IORP is right now working on. We see a lot of research happening in terms of ocean observations and all, but we are trying to, along with it, do the capacity building and trying to connect that science with the society through different and various activities through IORP and other opportunities and venues.
Okay, thank you. I see that Dr. Gadgil, you raise your hand. Is it to comment on this?
Yes.
Or do you want to answer the question that is addressed to you by Satish Shenoy in the chat box?
Oh, no. I want to just continue with the response to Srinivas's question, which is a very interesting one. I think there is a lot of hand waving going around when people talk of relationship of atmospheric convection to the ocean. Okay, particularly in deducing impact of climate change or ocean surface temperature change. I think Indian Ocean Panel must focus on process-based studies which will really tell us to what extent this warming of the Western Indian Ocean will have an impact on convection. For example, there is a study which shows that even if the SST warms, the threshold increases. So because the threshold increases, the convection really doesn't change. So there is a lot of assumptions that go into deductions on what will happen. And I think it is important for a panel like Indian Ocean Panel to also do some process-based studies, which will help in the long run in interpreting what is happening with climate change. Because otherwise, there's just too much hand waving going on, because you go from there to hand waving about the monsoon and even further hand waving on applications. So I think time has come to make the science a little more rigid as far as this ocean convection coupling is concerned and ocean monsoon coupling is concerned. Thank you.
Thank you. So we'll take the last question because we have 10 minutes left and we still need to address the two questions that have been set by the organizer. So the question is for you, Dr. Gadgil. How many monsoon got affected by Equino strongly, like the two that you had explained? This is a question from Satish Shenoy.
Yeah.
I can't hear you.
Sorry,
I think she's muted.
Unmute. Okay. If you look from 58, there were several. But if you look in the satellite period, there were only two. So vast majority of the extremes are explained by ENSO. It is correct. But the few in which it goes opposite to ENSO, that's what we need the prediction of. Because most models also don't predict Equino. They only predict ENSO, and the monsoon predictions are based only on ENSO. So unless, even though the extremes in Equino are not that frequent, unless we monitor Equino and predict it, we will not be able to get an accurate prediction of monsoon. Because, for example, 97, all the models went wrong. Strong El Nino, they all predicted deficit. They were totally wrong. So that is because of Equino. So I think if you want to get the predictions right, you have to worry about the minority also. Thank you.
Thank you very much. So we'll have 5 minutes to address the two questions in preparation of the UN Decade session at the end of the week, which are how to generate knowledge based to enhance understanding of ocean climate nexus. That's the first one. And what are the probable solutions to mitigate, adapt, and build resilience to the effect of climate change? So I don't know who wants to take the floor first, and we will probably continue the discussion, or at least refine our views on that by email because we won't probably have enough time. So who wants to take the floor first?
Well, I can give a quick input.
Roxy?
So, yeah, one of the limitations that I see so far is the disconnect between the risk, the observations and the modeling team. That prevents us from, connecting the processes that Sulojana was talking about. In fact, a lot of research has gone into process studies in the Indian Ocean and connecting, but this has to be transferred into when we make these climate models. These schemes and processes need to be redesigned as well as we redesign the observing systems also. And unfortunately, many of these observations that we are currently right now do not go into these models. That is another limitations. So that prevents us from improved forecasting. Like I said, there is data from the exclusive economic zones that are not public and henceforth are not used by many global models while simulating the monsoons or tropical cyclones or many of these events. So I think that connection between observations and modeling groups have to be strengthened. That's one point I would like to make. And the second point, quickly, is that we know that there has been a lot of reviews happening in the ocean base for the ocean basins. Like Indian Ocean had an independent review, Tropical Pacific had an independent review. Similarly, Atlantic also had an independent review. But many of these ocean basins interact. There is trans-basin interaction, and that has not been considered while we are reviewing and redesigning these huge observing systems. So many times we see those processes which are important for the monsoon and Indian Ocean climate, like the Indonesian through flow or the Agulhas or the Somali current, which connects to trans-basin or the water circulation. So these are not observed seamlessly across the trans-basins. So these are the two limitations that we need to work on. Thank you.
Thank you for sharing your views, Roxy. Are there other comments on these two items? I see.
Yeah,
yes.
So, can I show some slides, a couple of slides?
Maybe. Well, we have a couple of minutes, but we could try.
Yeah, sure. Yeah. Yeah. Are you able to see this?
Not yet.
You're able to see it?
It's coming. Yes, we can see it now.
Yeah. So this slide, yeah, this is this is from one of my colleagues. This is from the AR6, Prabir Patra. He has given me this slide about understanding the carbon cycle and climate feedback. This is based on the assessment of how much emission has happened. This is from the period 1960 to 2019. About 6.1 gigaton of carbon per emission. This is what has been emitted, mostly due to all the industrial activities. And the emission due to the land degradation, deforestation, this is about 1.4 gigaton of carbon per year. And nature has been absorbing the carbon because of the photosynthesis activity and the carbon cycle process. We have absorbed something like 2.4 gigaton of carbon per year, and the oceans are absorbing something like 24%, 1.8 gigaton per year. So what is remaining in the atmosphere this is known as the airborne fraction. The airborne fraction has been about 44%. This is 3.4 gigaton of carbon per year. So far nature has been very kind to us. So this is the important point. Can you see this slide?
Yes.
Now the proportion of carbon dioxide emissions that will be taken up by the land and ocean carbon sinks, this is again from the SPM of the IPCC, is smaller in scenarios with higher cumulative carbon dioxide emissions. So with further warming, right now we are something like the presently what we have absorbed, the ocean and atmosphere have absorbed something like 54%. This is what is of the carbon dioxide, and 46% is what is there in the atmosphere. And these are the high emission scenarios where the ability of the land and ocean to absorb the CO2 will keep decreasing as the emissions increase. So this is going to be a big problem. So clearly we cannot go, even the 245 scenario which we are currently following is clearly not sustainable. So we need to really go back to the very low emission scenarios. That is going to be a big challenge, how to mitigate. So we have to reduce the CO2 emissions. That is the main key point. And now this is also something in the India specific policy. India is one of the lowest per capita emissions in the world. If you see, because this is a more, if you want to go in terms of justice, the emission per India from India of carbon dioxide is very, one of the lowest compared to many countries. But when we look at the emission in terms of the per kilowatt, how much emission happens per kilowatt hour, that is basically the energy production efficiency and management, we are somewhere still on the very high. India is still very high. So this is basically what it suggests is India's per capita emissions are 60% lower than the global average, but the emission intensity of its electricity generation is among the highest. So this maybe if we can improve our energy production efficiency by maybe upgrading the technology of the power production, and also go for renewable energy. And renewable energy is already being promoted in India in a big way. And in fact, the International Solar Alliance, with our Honorable Prime Minister proposed in the COP26 meeting, this is going to be the key way to have the energy generation, and this will be key for really mitigating the effect of climate change. So he proposed one sun, one world, and one grid. So this is the key message. We have to go for renewable energy and more efficient ways of energy production.
Okay.
Yeah, thank you very much.
Thank you very much, Dr. Krishnan, for your suggestion. We will take note of that. I think we need to stop the discussion here. We are already late. And before we close the session, I would like to, first of all, remind that we will continue with the panelists to refine our view for the presentation on Friday. And I would like to thank the speakers for their talks and interesting discussion that we've had. I thank you very much. You want
and the IIOSC.
Yeah, thank you very much.
Thank you.
Bye-bye.
See you all again. Okay.
So thank you all the moderators, panelists. We had a very great discussions, and the learning from this session will be again presented in the plenary session on 18th March. That is on contribution to the United Nations Decade of Ocean Science for Sustainable Development. So in meantime, maybe all the moderators and panelists can work together to bring out the learning from this session. And I'll be soon sharing the recordings of this particular session, so that will be also useful for you. Thank you.
Anish, you might want to share a screen grab of the panelists, the picture.
Yeah, so if you can switch on your video. Professor Sulochana, if you can just switch on your video, we'll take a snap.
I'm trying to do it. It doesn't want.
We could see you until now, but
I know. In between, I switched it off because there was unnecessary. Look, it doesn't want to switch. It's okay. I'm trying. It's okay. I'm sorry. You can say absentee speaker.
Yeah, you can proceed with the grab and later put her picture over there from another screenshot or frame.
Yeah, it has come now.
Yeah.
Yeah. Okay. Thank you. Thank you all.
Thank you all.
The picture? Okay.
Thank you, Doctor.
Thank you.
Thank you. Good to see you.
Thank you. Bye.
Bye.